Overview of three-phase circuits. Did you know in the Philippines, unless otherwise marked, voltages are for three-phase systems? Well, three-phase systems are important for at least three reasons. First, nearly all electric power is generated and distributed in three-phase, okay, and is operating at a frequency of 60 Hz. Well, for Philippines, it's 60 Hz. In other countries like Japan, it is 50 Hz. Second, instantaneous power in a three-phase system can be constant, and that will result in uniform power transmission. Also, with this, there will be less vibrations of three-phase machines. Third reason, for the same amount of power, the three-phase system is more economical than the single-phase. Why? The amount of wire required for a three-phase system is less than that required for an equivalent single-phase system, so cost will go down. A three-phase system is equivalent to three single-phase circuits. So, if the voltage sources have the same amplitude and frequency, out of phase with each other by 120 degrees, then they are considered balanced. Okay? So we have here V sub AN, V sub BN, V sub CN. So these are voltages between lines A, B, and C and the neutral line. Okay? So here we can see a positive sequence. So meaning it's a counterclockwise sequence. By the way, phase sequence is the time order in which the voltage pass through their respective maximum values. So mathematically, okay, we have V sub AN, V sub VN, and V sub CN. So equal to V sub P bar 0 degrees, then another one V sub P bar negative 120 degrees, V sub P bar positive 120 degrees. So all of them, they are separated by 120 degrees, okay? And they have equal magnitude. Well, V sub P is the RMS value of the phase voltage. Okay? So next, this one is almost the same as the previous slide, but the difference is we have a negative sequence. So the sequence rotates in clockwise direction. So still, we have the same formula, but this time, previously it's V sub Cn. So today, right now we have V sub Cn. Previously it was V sub Bn, right? So they have different phase angles. Okay. So this one, V sub An is equal to V sub P bar 0 degrees, V sub Cn equal to V sub P bar negative 120 degrees, V sub Bn equal to V sub P bar 120 degrees. Okay. Next, we have a balanced load. So a balanced load has equal in magnitude and also in phase. So we have two configurations. We have Y connection and we have the delta connection. So Z sub 1, Z sub 2, Z sub 3, they are all equal, as well as Z sub A, Z sub B, Z sub C, they are all equal for delta. We can transform a Y to delta or delta to Y configuration with this relationship. Okay? So since both three-phase source and the three-phase load can be either Y or delta connected, then we can have four possible connections. We have Y to Y connection, Y to delta connection, delta to delta connection, and delta to Y connection. Let's have balanced Y to Y connection. So as you can see here, we have a source having Y configuration, a load having Y configuration. Here are the phase voltages and currents, and the line voltages and currents. Next, let's have balanced Y to delta connection. So basically, it looks like this one. We have a source having a Y configuration and a load having a delta configuration. These are the phase voltages and currents, and these are the line voltages and currents for a Y-delta connection. Next, let's have balanced delta to delta connection. So here for delta to delta connection, so source will be in delta configuration and also the source as well as the load. So the load has a delta connection. And here are the phase voltages and currents, line voltages and currents for a delta to delta configuration. Lastly, we have balanced delta to Y connection. So our source has a delta connection while the load has the Y connection. So the phase voltages and currents are this one, line voltages and currents this side. As you can see, there are so many formulas, right? I think we'll remember this better if you're going to apply instead. Agree?